BTEC Applied Science Unit 1 Physics, and I'm going to talk about waves on a string. I've already done a video about stationary waves, and in one of my videos about equations I've talked about this, but students find it difficult, so I'm going to spend a bit more time on it. Waves on a string, such as a violin or a guitar string. Now, when I pluck a guitar string, plectrum, pluck, two types of waves. We get transverse waves, which travel up and down the string. Transverse waves. You should remember transverse waves, the oscillations are perpendicular to the direction that the wave is traveling in. Then the string vibrates, and as it vibrates it produces sound, which is a longitudinal wave. So longitudinal sound waves travel through the air. Now these two waves, they will have the same frequency, but they will have different wavelengths, and I think this is a problem a lot of students have had, is that they get the two wavelengths muddled up. So I pluck a string, and we are getting transverse waves traveling up and down the string. Beautiful. So the string is plucked, transverse waves. Now what happens is that the waves travel to the end of the string and then they reflect. And then we get interference. So we get waves travel in both directions, they reflect, they come back and they interfere. And we get a very special type of wave called a stationary wave. A special type of wave called a stationary wave is produced, and the string vibrates in a loop. Think about these loops. Okay, so the string vibrates up and down like that, and the lowest frequency of this vibration is one single loop. So the length of the string is one single loop, and that's called the fundamental frequency, or the first harmonic. In music, the first harmonic is actually somewhere else. The first harmonic is there. But in physics, we say that the fundamental is the first harmonic. And for the first harmonic, for the fundamental frequency, the length of the string is equal to half a wavelength. Okay? So the lowest frequency is called the fundamental, or the first harmonic. We actually get lots of other frequencies produced as well. We get the second and third, etc. harmonics, but normally we don't notice them. They're in the background. Our ears just hear that lowest frequency, or rather we just notice the lowest frequency. But when I play that, in the background there's also that and that and that. You know, the other harmonics are there, and they make the tone of the instrument, they make it sound beautiful, but we don't really notice them normally, those other harmonics. We notice the fundamental, and the fundamental is a single loop. In the middle of the string it's vibrating a lot up and down. That's called an antinode, where the amplitude is maximum. And then at the ends of the string, where it's not vibrating at all, where the amplitude is zero, they're called nodes. So each loop is two nodes and an antinode. And as I said, I'm repeating myself, why not? Okay, the fundamental frequency is one loop. The second harmonic is two loops. The third harmonic is three loops. As I said, I've already done a video on that. Now, let's have a look at this simple little question here. A guitar string is 85 centimeters long. what will be the wavelength of the waves travelling along the string when it is vibrating in its fundamental mode. So you should be able to tell me. I will show you now. So we said that L equals lambda over 2 for the fundamental mode. For the first harmonic, L equals lambda over 2. So lambda, rearranging this equation, equals 2 times the length of the string, which will be 2 times 85, which I believe is 170 centimeters. In fact, there you go. Rub all that out and you might see it. Okay, so L is lambda over 2. Lambda equals 2 times L, which is 170 centimeters or 1.7 meters. If you're going to work out other stuff later on, it'd be a good idea to change it to meters. So now, to calculate the frequency of this stationary wave, what we would have to do first is work out the velocity of the stationary wave, which is how fast it's travelling, the speed. We call it the velocity, speed, same thing, probably. Now, the velocity depends on the tension in the string, and it depends on the mass per unit length of the string, which is basically how heavy it is. So the velocity depends on the tension. You will notice when I change the tension, the frequency changes because the velocity changes. So the velocity depends on the tension, and it also depends on how heavy the string is, the mass per unit length. This string here is a very light string. This string is much heavier. That's why it's okay. You get a different lower frequency. Because it's heavier, it doesn't vibrate as quickly. Okay? So the velocity depends on the tension and the mass per unit length. And this is the equation here. V equals root T over mu. Hopefully you won't have to rearrange it. Hopefully it will just be a case of working out the velocity. But V equals the square root of T over mu. T is the tension in newtons. Mu is the mass per unit length, kilograms per meter. Hopefully you'll be given it in kilograms per meter, not grams per meter, because then you'd have to change it to kilograms. So T divided by mu, and then get the square root. V equals root T over mu. We'll have a look at a couple of examples of that. Okay, let's have a go at a couple of examples. I'll go through this one slowly, carefully. A violin string has a mass per unit length of 0.0057 kilograms per meter. Now, I could have been cruel and said 5.7 grams per meter, and then you would have to divide it by 1,000 to get kilograms. But I've just given you grams per meter, sorry, kilograms per meter. The tension in a string is 49 newtons and its length is 32.5 centimeters. Calculate the velocity of the waves that travel through the string. Calculate the wavelength of these waves when it's in its fundamental mode. Calculate the frequency of the sound that these waves will produce. So the first thing we're going to work out is the velocity of the waves. So V equals root T over mu. Now, you don't need to learn this equation. You'll be given this equation in the exam. You're given all of the equations that you need. You might have to rearrange it. To rearrange it, you'd have to square both sides to get rid of the square root. It'd be a bit fiddly. Hopefully you won't have to do that. You'll just have to work out the velocity. Fingers crossed. So V is equals root T over mu equals the square root of T is 49 and mu is 0.0057 equals, so calculate the time, so 49 divided by 0.0057 equals, then square root that, equals, and I've done it wrong, do it again, 49 divided by 0.0057 equals, square root that, equals, that's better, 92.7 newtons, sorry, meters per second, 92.7 meters per second. Note, to get full marks, you need to write down the equation, bung in the numbers, work it out, 1 decimal place should do, meters per second, don't forget the units. The wavelength, now fundamental mode, we remember that the length of the string is half a wavelength. So for the fundamental mode, the length of the string is lambda over 2, so the wavelength is twice the length. So the wavelength will be 2 times 32.5, which will be 65 centimeters, which is 0.65 meters. Now you could leave it as 65 centimeters, but the next thing that we're going to do is work out the frequency. And to do the frequency, we are going to use the wave equation. Now, the wave equation, hopefully you remember V equals F lambda is the wave equation, very important. And so F is V over lambda, which is, and we've got V, is 92.7 divided by 0.65 is the wavelength, and we get a frequency of, so 92.7 divided by 0.65 equals 143 hertz. Don't forget frequencies measured in hertz, 143 hertz. And that's 3 sig figs, so I'm not going to bother with the decimal point. Okay, here's one for you to have a go at, and I suggest you pause the video and have a go at it. Okay, I'm going to do it now, assuming that you've already done it. So electric guitar, velocity of the waves, so I'm just going to zip through it. So V is root T over mu equals the square root of 76 divided by 0.0068. 0.68. Make my point a bit more obvious. Equals, calculate the time, 76 divided by 0.0068 equals square root equals 105.7, yeah, so 106, 3 sig figs is enough, 106 meters per second. Okay, the wavelength is going to be twice the length, so lambda is 2 times L, and that will be 2 times that, which is 1.3 meters, I believe. 1.3 meters, and then again F equals V over lambda. F equals V over lambda equals 106 divided by 1.3 equals 1.3 81.3. Hertz. Okay, so I hope that helped. If it did, say something nice in the comments. If it didn't, then probably do what you like. Okay, bye-bye for now.